Andrew Fitzgibbon, 3D computer vision, Microsoft.
Xue-Cheng Tai, I'm working on image processing, numerically also modeling. I'm now working at the Hong Kong Baptist University. I've just moved to there in May from University of Bergen, Norway.
Carola-Bibiane Schönlieb, University of Cambridge, Department of Applied Math and Theoretical Physics, working on inverse imaging programs from modeling to analysis and numerics and application.
Yeah, Ke Chen from Department of Mathematics Sciences, University of Liverpool. My interests are in image processing and computer vision.
Our program was about mathematical problems in gathering images from the world. These images might be MRI or CT or images from cameras or images from video. We want to discover the mathematical tools that let us deal with these images and let us analyze what's going on in them.
The title of the program is Variational Methods, New Optimization Techniques, New Fast Algorithms. So in fact, I think the program covers is image processing, computer vision, and machine learning, and the 3 workshops are also cover all those topics. So it's not only mathematics, there's a huge area of applications, both from image processing, computer vision, even image processing. You have many application areas, like you see EEE and medical. You see data, big data. I think all those topics are somehow covered in the program, and there are talks related to those topics.
Images are everywhere. In particular, nowadays, a lot of our decisions that we make, ideally in an automated fashion, rely on our ability to make sense of images. And so this is extremely timely with tons of applications in medical imaging. Xue-Cheng mentioned this, in decision making when you think of CCTV cameras, at airport security, identifying suspicious people, in automated driving, where you want an autonomous vehicle to drive you around. All of this is very much based on us being able to develop mathematical methods that can automatically detect the important bits and images and use them to make decisions.
This is imaging and vision. They are naturally interdisciplinary, and variational methods offer high-resolution solutions, if you like, and they naturally link applications to very deep mathematics. So this program brings on experts from different fields, and we can explore current state-of-the-art methods and future research. It's really exciting.
I think one is exciting. I think you see in the beginning some model was very difficult, but after a number of years of research, it's like what we're mentioning, and those models are solved. So everyone knows how to solve them. But this workshop, I think there are quite a number of other models are still very difficult at the moment for the industry. And it seems that there are new solutions, new methods coming up, and those are also one of the exciting points for the workshop, for the program.
I think imaging is an area where really, quite pure mathematics has quickly turned into practical algorithms that are used today. So we've seen in the past, like you were mentioning, some solved problems, maybe TV or minimization of TV. And what we really hope in this workshop is that some of the currently unsolved problems will turn into solved ones.
Exactly.
By the same procedure of pure mathematics leading to practical implementation.
So there are challenges on various fronts. First, when you're faced with an imaging application, an imaging problem, you have to come up with a good model or a good procedure to solve this problem. once you know the model, which is very often in mathematical terms posed in a continuous mathematical setting, how can you approximate this in a good way for doing computations with this? Can you do these computations efficiently, especially nowadays where we have so much and often very high dimensional imaging data? How can we computationally render this in a way that works efficiently and maybe even real time if we want to use this for some online decisions like I've mentioned before, autonomous driving. And then I think what is also quite dominating the program for the last couple of weeks, I think all of us have experienced this, is this emergence of machine learning methods that push themselves more and more into image processing and computer vision, solving formally solved problems with model-based approaches, all of a sudden with deep learning. And I think this balance and this interplay between model-based approaches and learning-based approaches is something that is one of the challenges, to find out what a good combination of those are for the next generation image processing computer vision methods.
One of the demands, challenges, is to require both high quality results and yet fast algorithm deliver results in real time. That requires a lot of deep mathematics and new algorithms. So usually we sort of manage to bring out the top experts from different fields to come together and discuss this field. Is really so interesting.
The challenge is the image processing computer vision coming from the real industry. So the challenge is really, you see, there are many problems they cannot, so at the moment they still cannot be solved. There is no good algorithm, there is no good model. So I think really in this workshop, many of the people are in the frontier to explore the unsolvable problems with a new model, a new algorithm. I think even many talks are related, as they both mentioned. I think this is one of the challenging, and we are seeing newer solutions, new ideas.
I'm definitely very excited by the focus that people are willing to have now on non-convex problems that previously we would have considered beyond analysis, and now we're making some decent progress in talking about non-convex problems.
Well, firstly, the applications are all over the place at the moment, from remote sensing and then satellite imaging to sort of micro levels like cell imaging, to medical imaging, different fields, security and CCTV, and where images are produced, like it's everywhere. And so the workshop will discuss, review these fields, and then we will talk about how we influence all these future development. We can give you some examples.
So one of the main problems with real applications is that the imaging data that you get is usually messy, noisy, incomplete, and so what can you do in terms of mathematical approaches to counteract that and still be able to extract an image where you can see something or extract some information from this image? One example is medical imaging. When you are taking a CT of a patient, you don't want to radiate him or her very much, ideally. And so the radiation is correlated with the messiness of the data that you get and with the incompleteness. And so when you want to radiate less, you get a lower resolution and lower quality measurement back, but still you want to look at a very high resolution image in the end. So how can you do this is something that we're thinking about in mathematical ways.
One thing you see that we have the Carola mentioned about the messy image. Another is that we have too many images. There are a lot of contents in the images. How do you learn the content from the image? And there are many talks. You learn the motion, you learn the contents of the image. And after learning all those things, I think there are many applications in the area we had been mentioned earlier.
Yes, I'm interested in applications where the cameras are used as sensors. For example, the camera can tell you where you are in the world. And again, if we understand the mathematics of how our images are formed, we can do a better job of using a camera as a sensor.
I think we have some very good exciting researchers which are staying here for a very long period, and many of the top researchers from the field are coming and staying. I think this is something very good, and I believe will produce it's a very cross-person, cross-discipline research from the program activities.
I think we could probably say that we probably expected machine learning and mathematics to interact a lot during the program, but it's interesting to see how far the ramifications spread. You know, when machine learning comes in, it induces a different mathematical view of the problem, which may then ripple on to how we can use what we already know, and how, if we ever need to develop new mathematics, here's the place to do it.
I think one more impact that I may mention is that imaging is a very visual and very approachable field. And so I think to convey that mathematics is exciting and that mathematics is useful, imaging is a very good way to do that. And so I think that could also have, and I think we had a public lecture by Joachim Weikert last week, has a very good impact also on showing the public that mathematics is useful and exciting.
This Newton program is much better than a lot of, say, international conferences where people are there for a short time. It's difficult to get hold of experts. Here we have resident experts staying here for more than a few weeks, some of them, and then researcher can really come in and discuss problem with them. And also, we have single track talks during the workshops. Really, we provide a lot of networking opportunities.